Imagine you run a social network with 1 billion users, and new accounts appear every single second. You want a vector for each person that captures who they are and who they connect to, because those vectors feed recommendations, fraud detection, and search. Early graph neural networks made that surprisingly painful because they needed the entire graph loaded in memory and had to be retrained from scratch whenever the graph changed. For a network that never stops changing, that is a non-starter. GraphSAGE from Hamilton and colleagues in 2017 fixed both problems, and its name quietly tells you exactly how. It samples and it aggregates. Let us walk through it together. To really understand the method, follow how GraphSAGE builds an embedding for a single node, step by step. Start by picking one target node, the person you want a vector for. GraphSAGE will not look at the entire graph to describe this node, and that restraint is deliberate. It only cares about the local neighborhood, the connections just a hop or two away, since those are what really define a node's context. Here is the first key idea: sampling. Some nodes, like a celebrity account, have millions of neighbors, so aggregating every one of them is simply hopeless. Instead, GraphSAGE randomly picks a fixed number of neighbors at each layer, which neatly bounds the work no matter how wildly popular a given node happens to be. Next comes aggregation, the second half of the name. The sampled neighbors' feature vectors get combined by a learned aggregator function, maybe a simple mean, a pooling operation, or even an LSTM. Notice what is really happening here. The model learns a reusable rule for combining neighbors, rather than memorizing one fixed vector per node. Finally, that aggregated neighbor summary gets combined with the node's own features to produce its embedding. Because it is a learned function of features, you can embed a brand new node the moment it appears, with no retraining at all. Now, to really see why this was such a big deal at the time, let us compare it directly against the graph networks that came before it. The earlier approach was transductive. It needed the entire graph loaded at once and learned a specific embedding tied to each existing node. So when a new node showed up, you had no vector for it, and the only fix was to retrain the whole thing from scratch. GraphSAGE is inductive instead. By learning how to generate an embedding from features and sampled neighbors, it produces vectors for nodes it never saw during training, and it does so on the fly. That is precisely what made graph learning practical at industrial scale, powering production systems like PinZage, the version Pinterest built on top of it. So if you remember nothing else, hold on to these 3 ideas that make the method work. First, neighbor sampling. By drawing a fixed size subset of neighbors at every layer, GraphSAGE keeps the computation bounded even when some nodes are wildly connected, which is exactly what lets it scale to enormous graphs. Second, learned aggregators. Rather than storing a fixed embedding per node, the model learns a function, mean, pooling, or LSTM, that turns neighbor features into a summary. That function is the reusable rule for generating embeddings. Third, it works inductively. Because embeddings come from features and neighbors rather than a lookup table, a fresh node gets a vector instantly. And remarkably, the same trained model even generalizes to entirely new graphs it has never once encountered before. Let us gather the essentials into 4 takeaways. GraphSAGE from Hamilton and colleagues in 2017 scales graph neural networks to massive, constantly changing graphs. Rather than aggregating every neighbor, it randomly samples a fixed number at each layer, which bounds the computation. It learns aggregator functions that generate embeddings from features, instead of memorizing one fixed vector per node. Because it is inductive, it embeds brand new nodes with no retraining, which is why it works at industrial scale. When you want ideas like this unpacked without the jargon, Standarity.com is where we break them down. Come join us.